All right, let's go. There is a question that every human civilization in recorded history has asked in one form or another. What was there before the beginning? For most of history, this was a question for priests and philosophers. Physics had nothing to say about it, because physics, by definition, describes the behavior of the universe that exists. Before the universe existed, there was nothing for physics to describe. That was the official position. That was the safe answer. That was what cosmologists told students and journalists and curious people for most of the 20th century. The Big Bang was not an explosion inside space, it was the creation of space itself. Time did not exist before it. Asking what happened before the Big Bang was like asking what is south of the South Pole. The question is malformed. There is no before. Time began at the moment of the Big Bang, and that is the end of the conversation. Except it is not the end of the conversation. Because when physicists pushed their equations harder, when they looked more carefully at the mathematics of the early universe, when they examined the cosmic microwave background with instruments precise enough to read the imprint of the first 300,000 years of existence, they began finding things, patterns, anomalies, structures in the data that should not be there if the Big Bang was truly the absolute beginning of everything. Signals that appear to carry information from before the moment when information was supposed to be possible. The universe, it turns out, may have left fingerprints. And some of those fingerprints are pointing backward in time, past the boundary that physics said could not be crossed. What follows is not mythology. It is not speculation dressed as science. These are 9 things that the mathematics of modern physics, combined with the best observational data we have, suggests happened before the Big Bang. Things that the standard model of cosmology says are impossible. Things that several of the most rigorous and respected physicists alive believe are real. Things that, if true, mean the universe did not begin. It continued. Number 1. A previous universe died, and we found its corpse. Roger Penrose is not a fringe scientist. He is one of the most decorated mathematical physicists of the 20th and 21st centuries. He proved, alongside Hawking, that singularities are inevitable in general relativity. He made foundational contributions to the mathematics of spacetime. He won the Nobel Prize in Physics in 2020. And for the last 2 decades, he has been arguing for a theory that most of his colleagues find deeply uncomfortable. Not because it is poorly reasoned, but because if he is right, the Big Bang was not a beginning. It was a transition. The theory is called conformal cyclic cosmology. The idea is this: our universe will not end in a dramatic collapse. It will end in silence. Trillions upon trillions of years from now, the last stars will exhaust their fuel and go dark. The galaxies will dissolve. The only structures remaining will be supermassive black holes, slowly consuming the last dust and radiation. And then, over spans of time so vast they make the current age of the universe look like a single breath, even the black holes will evaporate through Hawking radiation, releasing their mass back into the universe as a thin, cold gas of photons. What remains, at the absolute end of everything, is a universe populated entirely by massless particles moving at the speed of light through an endlessly expanding void. Here is where Penrose's mathematical insight becomes genuinely vertiginous. For massless particles traveling at the speed of light, according to the equations of special relativity, time does not pass. Distance does not exist. A photon does not experience the journey between 2 points. It exists at both simultaneously. In a universe where everything remaining is massless, the concepts of scale, distance, and the passage of time break down completely. An infinitely vast, cold, dark, dead universe becomes, in the language of conformal geometry, mathematically indistinguishable from an infinitely hot, dense, compressed singularity. The end state of one universe and the initial state of the next are the same geometric object described from different perspectives. The previous universe did not create our Big Bang. It became our Big Bang. But Penrose went further. He predicted that if this is true, the death of that previous universe left physical scars. When supermassive black holes evaporated in the universe before ours, their evaporation events released concentrated bursts of energy that would have imprinted concentric rings of anomalous temperature variation on the cosmic microwave background of our universe. These rings are called Hawking points. In 2018 and again in 2020, Penrose and his collaborators published analyses of the Planck satellite's cosmic microwave background data, claiming to have found these rings, hundreds of them, distributed across the sky, with statistical properties that, according to their analysis, cannot be explained by the standard model of inflation. The debate over whether these rings are real signal or statistical artifact is ongoing and fierce. But the fact that we are having this debate at all, that we are looking at the sky and asking whether we can see the dying heartbeats of a universe that existed before ours, is itself a revolution in how physics thinks about the boundary of time. Number 2. The quantum vacuum was never empty, and it was unstable. Before the Big Bang, according to the standard model, there was nothing. Not empty space, not a dark void. Nothing. Not even the absence of something, because absence requires a location, and locations require space, and space did not exist. But quantum mechanics has a profound problem with nothing. In quantum field theory, a perfect vacuum, a region of space with zero particles, zero energy, zero everything, is not a stable state. It cannot be. The Heisenberg uncertainty principle forbids it. The uncertainty principle states that the more precisely you know the energy of a system at a given moment, the less precisely you can know it at a future moment. A system with exactly zero energy at all times would violate this. Therefore, even a perfect vacuum seethes with quantum fluctuations. Virtual particles appear and annihilate. Energy borrows itself from the future and repays it. The vacuum is not empty. It is a churning, probabilistic foam of potential. This is not theoretical. The Casimir effect, measured in laboratories with extraordinary precision, demonstrates the physical reality of vacuum energy. Two uncharged metal plates placed close together in a vacuum experience a measurable attractive force, caused by the suppression of vacuum fluctuations in the space between them. The vacuum pushes. The vacuum is real. Now apply this to the moment before the Big Bang. If there was no space, no time, no matter, no energy, the state of absolute nothing was itself a quantum system. And quantum systems cannot remain in their ground state. They fluctuate. Physicist Alexander Vilenkin at Tufts University has developed a rigorous mathematical treatment of what he calls tunneling from nothing. In this framework, the universe literally quantum tunneled into existence from a state of absolute non-existence, in the same way that a radioactive nucleus spontaneously decays by quantum tunneling through an energy barrier. There was no before in the sense of a time that elapsed. The universe appeared not because something caused it, but because, in quantum mechanics, the probability of its appearance was non-zero. And in a timeless quantum state, anything with a non-zero probability of occurring does occur. The unsettling implication is that the pre-Big Bang state was not a void. It was a quantum condition of pure mathematical potential, and it was inherently, structurally, inevitably unstable. Our universe was not created. It leaked into existence. Number 3. Inflation did not start here. It was already running. The theory of cosmic inflation was proposed by Alan Guth in 1980 to solve several problems with the standard Big Bang model. It proposes that in the first fraction of a second after the Big Bang, space underwent a period of exponential expansion, doubling in size every tiny fraction of a second, driven by the energy of a field called the inflaton. This rapid expansion smoothed out the universe, explaining why it looks so uniform on large scales and why its geometry is so flat. Inflation works. It matches the data. It is one of the pillars of modern cosmology. But when physicists examined the mathematics of inflation in detail, they found something alarming. Once inflation starts, it is almost impossible to stop it everywhere at once. In any region of the inflaton field, quantum fluctuations will occasionally cause the field to drop to a lower energy state, ending inflation locally and producing a Big Bang. This is how our universe formed. But while our region was ending inflation, surrounding regions were still inflating. And inflating regions expand faster than the bubbles of ended inflation can grow. The inflationary ocean does not drain. It expands forever, producing an infinite and eternal sea of still inflating space from which bubble universes like ours continuously nucleate. This is eternal inflation, and its implications for what existed before our Big Bang are staggering. If eternal inflation is correct, then before our Big Bang, inflation was already happening. Not here, not in our bubble, but in the larger inflationary field from which our bubble emerged. Our Big Bang was not the beginning of expansion. It was a local transition. A phase change in a pre-existing inflationary medium that had been running for, possibly, an infinite amount of time before our bubble separated from it. The Big Bang was not a beginning. It was a nucleation event. like a bubble forming in a glass of carbonated water. The glass was already there, the water was already there, the pressure was already there. Our universe popped into existence inside a pre-existing structure, and that structure shows no signs of having had a beginning of its own. Number 4, the universe has a handedness, and it came from before. Look at your hands. They are mirror images of each other, but not identical. You cannot rotate one to match the other. This property is called chirality, or handedness, and the universe has it too. In particle physics, the weak nuclear force, the force responsible for radioactive decay, violates what is called parity symmetry. It has a preference. It interacts preferentially with left-handed particles over right-handed ones. This asymmetry is built into the standard model of particle physics. It is real, it has been measured to extraordinary precision, and it is deeply mysterious. The question that bears directly on the pre-Big Bang epoch is this: where did this asymmetry come from? In a universe that began from a perfectly symmetric singularity, all directions, all handednesses, all orientations should have been equivalent at the moment of creation. There should be no preferred chirality. The universe should be symmetric under mirror reflection. But it is not. Some theoretical physicists, working in the framework of loop quantum cosmology, have proposed that the handedness of our universe is a fossil, an artifact of the bounce. In loop quantum cosmology, the Big Bang was not a true beginning, but a quantum bounce, a moment when a previous contracting universe reached maximum density and rebounded. The contraction and expansion are not symmetric. The contracting phase carries information about the chirality of matter and energy in the collapsing universe, and this information survives the bounce, imprinting the handedness of the pre-bounce universe onto ours. If this is right, the reason the weak force prefers left-handed particles is not something that arose spontaneously at our Big Bang. It is a memory, a structural preference inherited from a universe that existed before, that collapsed, that bounced, and that passed its asymmetry forward across the boundary of time like a genetic trait passed from parent to child. The universe is left-handed because its parent was left-handed. And that parent had to exist before the moment physics says nothing could exist. Number 5. Dark matter was already there. It did not form with us. Dark matter is one of the most well-established mysteries in modern astrophysics. We cannot see it. We cannot directly detect it. We have never captured a single dark matter particle in any laboratory on Earth. But we know it is there because we can see its gravitational effects. Galaxies rotate at speeds that only make sense if they are embedded in vast halos of invisible mass. The large-scale structure of the universe, the web of filaments and voids and galaxy clusters, matches simulations only when dark matter is included. Without it, our models of cosmic structure fail completely. The standard assumption is that dark matter formed in the very early universe, shortly after the Big Bang, as some kind of particle species that coupled only weakly to normal matter and radiation. But there is a growing body of theoretical work suggesting that this assumption may be wrong. A class of dark matter candidates called ultralight axions, or fuzzy dark matter, have quantum mechanical properties so extreme that their behavior on cosmological scales is dominated by quantum pressure rather than classical gravity. The characteristic scale of their quantum behavior is comparable to the size of entire galaxies. And some models of axion production suggest that axions were not created in the hot plasma of the early universe. They were created earlier, during inflation, or even before inflation, in a pre-Big Bang phase. If this is correct, dark matter is not a product of our universe. It is a visitor from before it. The invisible scaffolding around which every galaxy formed, the gravitational architecture that made structure in the cosmos possible, was already in place before the Big Bang. It arrived in our universe as a relic of the inflationary epoch, or of whatever preceded it, and it has been shaping cosmic structure ever since, while remaining completely invisible to every instrument we have built to search for it. The skeleton of the cosmos predates the cosmos itself. Number 6. The cold spot is a bruise from a collision with another universe. In 2004, the WMAP satellite produced the most detailed map of the cosmic microwave background available at the time. The cosmic microwave background is the afterglow of the Big Bang, the faint thermal radiation that fills the entire sky uniformly at a temperature of 2.7 Kelvin. It is the oldest light we can see. It contains information about the state of the universe when it was only 300,000 years old. In the southern hemisphere of the CMB sky, there is an anomaly. a region approximately 1 billion light-years across that is measurably colder than its surroundings. Not slightly colder, 70 microkelvin colder, which, in the context of CMB temperature variations, is an enormous deviation. The probability of this feature arising by random chance in the standard inflationary model is less than 2%. It should not be there. Astronomers proposed that it might be caused by a supervoid, a massive empty region of space in the direction of the cold spot that would drain energy from photons passing through it, via the integrated Sachs-Wolf effect. Observations found a void in that direction, but it is not large enough or empty enough to account for the full temperature depression. The void explains part of the anomaly. It does not explain all of it. Laura Mersini-Houghton at the University of North Carolina has proposed an explanation that reaches back before the Big Bang. In the framework of eternal inflation, our universe formed as a bubble, nucleating in an inflating pre-existing field. Other bubbles also nucleated. If our bubble collided with a neighboring bubble universe during or shortly after our formation, the collision would have left a specific imprint on the CMB, a region of anomalously low temperature, a circular scar in the sky. The cold spot in this interpretation is not a statistical fluke. It is not a void. It is a bruise. Physical evidence imprinted on the oldest light in the universe of a collision with a neighboring universe that occurred before our Big Bang was even complete. A neighbor we will never see, never reach, and never communicate with, but whose impact on us was so violent that we can still feel it. In the temperature of the sky, 14 billion years later. Number 7. Gravitational waves from before the Big Bang are already passing through you. In 2023, multiple pulsar timing array collaborations around the world, including Nanograv in North America and PPTA in Australia, announced simultaneous detection of a gravitational wave background. Not individual gravitational wave events from specific merging black holes, but a diffuse, omnipresent hum of gravitational waves filling all of space at all times. A cosmic rumble, too low in frequency for LIGO to detect, but measurable by watching the precise timing of pulsars distributed across the galaxy. The most straightforward explanation for this background involves supermassive black hole binaries in the centers of merging galaxies. These exist, and they should produce gravitational waves. The question is whether the detected signal is fully explained by them. Several theoretical groups have published analyses suggesting that the Nanograv signal contains contributions that cannot be attributed to astrophysical sources in our universe. The spectrum of the signal, its distribution across frequencies, has features that match predictions for gravitational waves produced in the pre-Big Bang epoch. Specifically, from processes occurring during or before cosmic inflation, when the density and temperature of the universe were so extreme that the space-time fabric itself was violently disturbed. If gravitational waves can be produced before the Big Bang, and if they can survive the transition through the Big Bang into our universe, they would be the most ancient observable in existence. They would carry direct physical information about conditions before the beginning. Every instrument that detects them, and right now the entire Earth is passing through this background every second, would be receiving a signal from before time began. The universe may be speaking to us about its own prehistory. We are only now learning to listen. Number 8. The arrows of time point to a mirror universe running backward beside ours. In the standard model of the Big Bang, time has a direction. Entropy increases. The universe moves from order to disorder. This is the second law of thermodynamics, and it is inviolable. We experience time flowing forward because the entropy of the universe is increasing in that direction. Toward the Big Bang, entropy was lower. Away from it, in our future, entropy is higher. This gradient defines the arrow of time. But this raises an immediate and devastating question. Why was entropy so low at the Big Bang? The initial state of the universe was one of almost perfect smoothness, almost perfect uniformity, and almost perfect thermodynamic order. This is an extraordinarily improbable configuration. If you prepared the universe randomly from the space of all possible states, the chance of getting one as ordered as ours was at the Big Bang is so astronomically small that no number we have language for can adequately express it. Roger Penrose estimated this probability as 10 to the power of 10 to the power of 123, a number so vast that if you wrote a 0 for every atom in the observable universe, you would not have enough zeros. The question is why the Big Bang started in such an improbable low entropy state. One answer comes from theoretical physicists Julian Barber, Tim Kozlowski, and Flavio Mercati, who in 2014 published a paper showing that in a gravitational system with no initial entropy constraint, the natural midpoint of any trajectory in the space of possible states is a region of minimum size and maximum uniformity. Both sides of this midpoint see time flowing outward from it, with entropy increasing in both directions. The implication is shattering. Our Big Bang was not the beginning of time, it was the center point. The minimum entropy configuration from which time flows in two opposite directions simultaneously. In one direction is our universe, with time flowing forward, entropy increasing, galaxies forming, stars burning, life evolving. In the other direction is a mirror universe, running backward in time relative to us, also with entropy increasing in its own temporal direction, also containing galaxies and stars and potentially life, moving in the opposite direction along the time axis. This anti-universe is not somewhere else in space. It is not in a different dimension. It is the other half of the same solution to the same equations. It existed before our Big Bang in the only meaningful sense of before that applies, when time itself bifurcates at a single point. Physics does not just permit it. Physics may require it. Number 9. The constants of physics were set before the Big Bang, and they could have been different. The universe runs on numbers, fundamental constants, the speed of light, the gravitational constant, the fine structure constant that determines the strength of electromagnetism, the ratio of the electron mass to the proton mass, the cosmological constant that governs the energy of empty space. There are approximately 26 of these numbers in the standard model of physics. None of them has a theoretical explanation. None of them can be derived from more fundamental principles. They are simply what they are, measured, encoded in our theories, and left unexplained. The disturbing fact about these constants is how precisely calibrated they are for the existence of complexity. If the strong nuclear force were 2% stronger, protons would not form. If the cosmological constant were larger by 1 part in 10 to the power of 120, the universe would have expanded so fast after the Big Bang that no structure could ever have formed. If the fine structure constant were slightly different, atoms as we know them would be impossible. Life, chemistry, stars, planets, all of it balances on the knife edge of these numbers. In the framework of the string theory landscape, this is not a coincidence, and it is not by design. It is selection. String theory produces not one universe with one set of constants, but a vast mathematical space of possible universes, each with different values of the fundamental constants, each with different physics, each with different structures of space and time. Most of these universes are dead. The constants are wrong. Atoms cannot form, or stars cannot burn, or the universe collapses before anything can happen. Our constants were set during the inflationary epoch, or possibly before it, by the specific way our bubble universe nucleated from the pre-Big Bang inflationary field. Different bubbles, different constants. The constants are not logical necessities. They are outcomes of a random process that occurred before our universe existed, in a pre-Big Bang landscape that is still generating universes right now, constantly, in regions of inflating spacetime forever beyond our ability to observe. What happened before the Big Bang in this framework was a lottery, an infinite, eternal, ongoing lottery. And the specific set of numbers that describes our reality, that permits stars and carbon and biology, and the fact that you are here to read these words, was drawn in that lottery before our universe was born. The laws of physics themselves are a fossil of the pre-Big Bang epoch, not eternal truths. Lucky outcomes. These 9 things, a dying previous universe leaving rings of light in our oldest data, a quantum vacuum too unstable to remain nothing, an inflating pre-existing field that was already running before our Big Bang began, a handedness inherited from a pre-bounce cosmos, dark matter predating our universe entirely, a bruise on the oldest light from a collision with a neighboring reality, gravitational waves still humming from before the beginning of time, a mirror universe running backward beside ours from a shared origin point, and fundamental constants set by a pre-Big Bang lottery we will never observe. They are not science fiction. They are the conclusions that fall out when the mathematics of modern physics is taken seriously and followed past the boundary where intuition stops working. Physics says all of this is impossible. Physics says time began at the Big Bang. Physics says there is no before. And yet the equations keep pointing backward. The data keeps showing structures that should not be there if the standard story is complete. And the physicists who are honest about what their own mathematics is telling them keep arriving at the same uncomfortable conclusion. The Big Bang was not the beginning of everything. It was the beginning of everything we can see. What lies beyond it, what preceded it, what left its fingerprints on our oldest observable data, is not nothing. It is a territory that our physics is only beginning, slowly and reluctantly, to map. The universe did not come from nowhere. It came from somewhere. And that somewhere, whatever it was, left traces. We are only now learning to read them. If you want to see more videos like this, click the video on the screen now.